This is titled Modern Science, Not Having a Method, but Having a Tool in Algebra and Calculus, and what mathematical physics can't answer, or what calculation can't be used for. Subtitled, The Limits of Mathematical Physics. CONTRA, Algebra, Calculus, and the Scientific Revolution. If physics was the primary subject matter of the new science of the 17th century, and not, as I think, rational mechanics, why do we find a scarcity of treatises of physics surrounding the scientific revolution? Why, I mean, did so few early modern philosophers write about physics in a way that covers the subject as a whole? That is, from the time when the new science was brought forth with the astronomical theories of Copernicus, and speculative thought amongst those who went by the name of natural philosophers contended with the Scholastics, only a few works in what was previously called physics were produced, when we would expect the subject matter to be focused there. Now, I know that is rather surprising. It is a surprising claim to say that there were not treatises of physics. I will explain why I make that claim. There is obviously a difference in paradigm between Aristotelian and modern physics, and that discipline is approached with different methodologies. Perhaps, however, restricting the domain of physics to what can be explained mechanistically or even mathematically obfuscates the very subject matter, such as to result in a different science, or a different science of a different subject matter. My interest here is that certain fundamental questions, difficulties which the entire of Aristotle's physics is developed to resolve, are not even mentioned in early modern physics. And the more foundational to physics scholastic dilemmas are, the more so they are ignored. For instance, Aristotle considers what is required for there to be change. What is required for there to be change, for there even to be such a thing as change? What else must there be prior to that? This is required because change is something obscure, as is time. One part of time, the past, no longer is. And the other part, the future, is not yet. While the nows, or moments, or instances, are indivisible points. And there cannot be change from one thing to another at an instant. But change can only take place between different instances. For the thing has to be in one state at one instant. The thing changing has to be in one state at one moment and in another state at another moment for it to have changed. That is, to even notice that something has changed, what is required is that that thing was at one instant, or at one point in time, or at one time, in one state, and at another time, in a different condition, such that a lapse of time must have occurred in which the change took place. That is to say that there cannot be change at an instant, not from something to something. Likewise, something changing, something in the process of change, is no longer what it was, nor yet what it is becoming while changing. These are obscure concepts which require much conceptual leveraging. Clarifying those sorts of concepts which are foundational to physics, comprises a great deal of Aristotelian physics. Yet those dilemmas or difficulties are not touched upon in early modern or in modern physics. Nor is there any speculation that certain theories are foundational at all. Hardly any moderns wrote of physics as an entire discipline and subject matter in an encompassing way. Their theories arise and disappear again in isolation without reference to other theories, in the sense of some of them being prior and more foundational to others and some posterior, such as to reference principles of physics. The scientific theories do not form an integral whole. In fact, often previous theories which once formed a core part of their theoretical structures are repurposed as scaffolding for others and then thrown out and discarded. Besides that, science has abandoned nearly every one of its own theories, something that should be absolutely discrediting. What is revealed is that there is no scope encompassing the subject matter as a whole. I would even call into question whether the subject matter of physics survived the scientific revolution, and if what emerged afterwards was not an entirely different subject of study. Chief amongst the changes that took place at that time was the desire to restrict the subject of physics to what can be explained mechanistically and mathematically. Thus, Huygens said that in the true philosophy, one considers the cause of all natural effects in terms of mechanistic motions. This, in my opinion, we must certainly do, or else renounce all hopes for ever comprehending anything in physics. And Robert Hooke said that neither can the mind itself, at least as to physical matters, be allowed to apprehend that whereof it has not in some sense a mechanical conception. While Leibniz, in 1671, said that, quote, all modern philosophers desire to explain natural phenomena mechanistically. And Descartes, identifying physics with a branch of mathematics, identifying physics with a part of mathematics, thought that the only permissible questions, the only definite questions, were those in which ratios can be transmuted into equations. But I ask, does a subject once mathematicized remain the same subject matter? Or would a physics reduced to what can be formulated mathematically be converted into an adjacent discipline, such as that of rational mechanics? The reason for this inquiry is that very few early modern natural philosophers wrote treatises on physics in the manner of that of scholastic physics, in a way that encompasses the entire subject matter. And those few that did, or that approximated that sort of project, are rather termed philosophers nowadays, instead of natural philosophers and scientists, and are known to be such. Besides Hobbes, Descartes, and Boyle, most of the activity which gets classed as being concerned with physics was fragmented and isolated, such that the principles of physics are not mentioned, nor are the conceptual difficulties at the foundations of motion and change and becoming, or generation and corruption. There is no mention of such things. What the natural philosophers of the scientific revolution were overwhelmingly interested in was developing nuanced mathematical procedures. We will inquire into what those mathematical procedures, I mean the infinitesimal calculus and algebra, are for and what function they have, as well as what they cannot be meant and used for. That is nearly what their focus is and what their subject matter is, or should reveal that to us. I mean in this to stress the importance of what might be considered a mathematical revolution, in which algebra and calculus emerged at the expense of classical geometry and arithmetic, and became instruments for a mathematical physics, something which happened prior to their physical speculations, or at least alongside. Thus, alongside the attempt to restrict physics to what can be formulated after the manner of rational mechanics, a more mathematical discipline, there also were developed new mathematical procedures to perform the task of adapting physics to mathematics, or vice versa. J.L. Hilbrun, in The Elements of Early Modern Physics, gives a clue to the significance that algebra and calculus had for the new science of the 17th century. Quote, during the 1690s, Malebranche climbed still further by mastering the Leibnizian calculus, an instrument more effective in hunting out the truths of physics than even the analytic geometry, that is algebra, of Descartes. As he says that the Leibnizian calculus is an instrument even more effective in hunting out the truths of physics than analytic geometry or algebra, which was designed by Descartes. Again, these mathematical procedures were designed towards physics and by figures like Descartes, Leibniz, although calculus and algebra were the epicenter of the intellectual activity in the 17th century, even in the 16th century. And to continue the quote, Malebranche was joined in these studies by a group of strong mathematicians, later his colleagues in the academy, all also Cartesian in physics, of whom the best known are Pierre Verignon and Marquis de Hospital. Fontenelle shows us each of these men traversing the same road to enlightenment, from scholastic night through Cartesian day to the blazing light of the differential calculus. Their example and their work were to influence the mathematical physicists of the mid-century, D'Alembert, Marpetuse, and even Euler. End of quote. Mark that the road that these men traversed to enlightenment was from scholastic night through Cartesian day to the blazing light of the differential calculus. That shows the significance that these mathematical procedures had for a mathematical physics, for science. But the mathematical procedures of algebra and calculus quite obviously stick out as the most distinguishing aspect of modern thought. These mathematical procedures are obviously the distinguishing aspect of science, or the post-scientific as an Aristotelian, looking at these sorts of processes of physics and how physics is performed, what those theories look like. They're in algebraic equations, as the scientific formula are presented in algebraic equations. That is just what Descartes intended in his rules for conducting the mind. To sort of find a mathematical set of procedures that can adapt anything that can be quantitative, anything that can be measured and quantified, to adapt every problem to that Even Leibniz somewhere said that he thought that every problem will one day be able to be reduced to equations, mathematical equations. These quote-unquote rationalists, Leibniz, Descartes, and many who laid the groundwork for those sciences. There was much activity in calculus and algebra before those men. I mean to say that a difference in methodology, I stress that fact because a difference in methodology, such as the experimental method, is not adequate to account for the primary dilemmas of scholastic physics not being considered, nor for the same questions not being answered at all, nor for scholastic physics appearing as an entirely different subject matter from that which followed. That is to say, that the experimental method does not account for the sorts of changes that occurred in the discipline of physics. The total mathematization of physics is not explained by merely testing the prior dogmas with experimentation. The reformulation of physics into a discipline which only employs the concepts relevant to rational mechanics, as they universally claimed, to reformulate physics into a discipline which only employs the concepts relevant to rational mechanics. That would, however, adequately account for such a change. But that implies a preference for what can be mathematically formulated, and the emergence of algebra and calculus, especially with their significance for a mathematical physics and their employment therein, appear as their instruments or tools, even simply as their procedures, but as things more qualified to differentiate and distinguish the new science than any supposed method. Those are their instruments or their tools, these mathematical procedures, which are of more significance to the discipline of science than anything like an experimental method, which would not account for the sorts of dilemmas in Aristotelian philosophy, Aristotelian physics, whether motion is continuous or discrete, and those that follow from them. A great many conceptual difficulties simply being ignored. And for the eventual presentation of scientific formulae as algebraic equations. Again, the natural philosophers at the dawn of modernity were uninterested in offering theories of physics contrary to those of the scholastics. They are uninterested in contending with them about their conceptual difficulties. They did not come out of the same conceptual difficulties with opposing views. They were uninterested in participating in those sorts of dilemmas, the problems at the foundations of physics for Aristotle, the conceptual difficulties. Are things not mentioned in modern physics. They were not even regarding the same sorts of questions. I mean that what fragmented and isolated physical theories were produced may well fall under the category of rational mechanics, rather than what the scholastics would have thought of as physics. For the scholastics had a category of rational mechanics. And from my perspective, a great many scientific theories, in fact, the whole scientific project, looks like an expansion of rational mechanics, or an adapting of that to a more numerous set of problems. But in that manner in which rational mechanics was performed by Archimedes and others. Yeah, in any case, modern science in the 17th century, the treatises on physics, the works in physics, the theories in physics were not compiled in a rounded off way that has in scope the whole subject matter of physics. Hardly any of the natural philosophers of early modernity had anything to say about the dilemmas of physics which previously formed the backbone of that subject, such as, again, whether motion is continuous or discrete, whether alteration is different from generation and corruption, or all change is coming to be, whether composite bodies are formed from simple elemental bodies, and so on. For example, they offer no account of generation and corruption, which is obviously an important part of nature. If you're going to design a science of nature, you ought to at least be able to give an account of generation and corruption, at least to say whether that be different from qualitative change, or if all qualitative change is coming to be and passing away. They were not operating within the same subject matter, but within a different field of thought that falls somewhere alongside and adjacent to, but is not physics. In hindsight, Aristotelian physics appears as a theoretical physics, nay, more so even a speculative physics, in comparison with the new science of the 17th century. In fact, all of what were then classified as theoretical sciences appear in hindsight as speculative sciences, or as speculative philosophy, even though they met the standards of demonstrative reasoning. Not only are the methodologies different, but even that the sorts of difficulties which are resolved, the sorts of questions asked and answered, are unfamiliar and dissimilar. But Aristotelian physics appears to fall under the category of a speculative science, or a speculative philosophy nowadays, because many of the dilemmas are conceptual difficulties. Not that they are abstract and irrelevant to concrete things, but rather that the foundations of physics are necessarily thus. Again, whether there can be motion at an instant, motion in the now, whether there can be motion in the now. Is a conceptual difficulty. It can only be resolved conceptually. But it's not abstract and irrelevant to concrete things. Yet those conceptual dilemmas were surprisingly neglected and bypassed entirely in early modern physics. Even where there is overlap and disagreement between scholastic and modern physics, those places are marginal and not numerous. They are rather few. A greater part of the difference between modern and scholastic physics is attributable to the turning towards different questions and to admitting only mechanistic and mathematical explanations, such as to render the entire subject of physics unrecognizable. Physics was before then the science of change and motion, science of nature, a theoretical science concerning the principles of nature, the principles of change and motion, as whether time is composed of instances, whether spans of time, that is, are composed of instances, whether motion at an instant is possible. That one is important because in calculus, there is the notion of instantaneous velocity, of things being moved at an instant, of changing within the now at different rates of speed. When something cannot be said to have changed unless it was at a previous instant different than at a later instance. Even for there to be change, there has to be a lapse between two times when something was in different conditions. But they speak of instantaneous velocity in calculus as oblivious to all the conceptual difficulties. We have there one of the most, by definition, contradictory. Has to be an example of, by definition, contradiction, or being contradictory by definition, more so than any other contradiction. That one stands out as the best example of contradiction, of instantaneous velocity, and of measuring speeds in terms of how fast and how fast they were moving at that instant. An infinitesimal but these were always of significance. At the time of Galileo's trial, calculus was outlawed. The Jesuits made calculus illegal to teach in public because of these conceptual contradictions of instantaneous velocity, infinitesimals in all aspects, and that there were attacks upon them and that they were never met. Hobbes also contended against them. Bishop Berkeley, George Berkeley, contended against calculus in the Analyst, addressed to an infidel mathematician. These great philosophical works were never even stressing the conceptual difficulties at the foundations of calculus and algebra. That was always there was the contention between geocentric and heliocentric cosmologies, but there was in mathematics a contention between Euclidean geometry and algebra and calculus, and those were outlawed. But again, physics was, to the scholastics, a science concerning things like whether time is composed of instances, whether spans of time are composed of instances, whether motion at an instant is possible, whether change is continuous or discrete, or in other words, whether processes of change are infinitely divisible, how motion and change are even possible, or what would be required for there to even be such a thing as motion, which motions are primary and which dependent upon and consequent to others, whether the circular motion of the heavens, whether the circular motions of the luminaries are eternal, and what their relation is to the upwards and downwards rectilinear motions of fire and earth, whether a change in the qualities of warmth, coldness, moisture, and dryness can account for the changing of water into air, or the generation and destruction of simple bodies. And importantly, whether the receding and advancing seasonal motion of the sun accounts for those qualitative alterations as well as of generation and corruption in general. That is Aristotle's account of generation and corruption as being caused by the oblique motion of the sun while going circularly through the zodiac, moving slightly more north in the summer and more south in the winter to account for, obviously, the destruction or the corruption of vegetative life and much else, and then the regeneration of vegetative life in the spring and summer. That this generation and corruption was attributed to the sun based on mathematical, even based on syllogistic reasoning. Those were the sorts of things which physics was before then concerned with. The new science, although concerned also with motion, was notably different. Many, if not all, of those dilemmas were ignored, such that the entire subject matter of physics seems to have been diverted to questions of a different sort. One might attribute the difference to including much that is practical, but I don't think that is a sufficient explanation, even though there was an impulse to practical invention. For even mechanics was a mathematical science and intended to avoid being classed as practical. Even mechanics aimed at being a theoretical science, unlike perhaps engineering today. Mechanics then was not equivalent with the mere designing of machines. Perhaps part of the difficulty is that the distinctions were blurred upon reformulating a new physics after the model of rational mechanics. In any case, what cannot be explained by the fairy tale version of science as a turning away from dogma towards observation and experiment is the function and use of the infinitesimal calculus in algebra. Again, what cannot be explained by the fairy tale version of science as a turning away from dogma towards observation and experiment is the function and use of algebra. The fairy tale version of science says that they were turning away from dogma towards mere experimentation. But that wouldn't get them to scientific formulae being presented as algebraic equations, merely turning towards observation and experiment. It would have no effect, would merely result in bad physics. what cannot be explained by the fairy tale version of science as a turning away from dogma towards observation and experiment is the function and use of the infinitesimal calculus and algebra. How are they related to the new science? What is their subject matter? What, that is, are they applied to? Or better yet, what do they apply the measures of number and shape to? One cannot help but finding these nuanced mathematical procedures as entirely obscure, even as to their content and purpose. There is a naive progressivism that characterizes them as more advanced than classical geometry and arithmetic, and what is worse, that characterizes them as being more pure forms of mathematics than the sciences of shape and number in and of themselves. For operating with symbols, which might indifferently represent numbers, lengths, areas, spans of time, velocities, or anything that can be quantified, they are misconceived as being more abstract. Again, for operating with notation, a sort of notation, which might indifferently represent numbers, lengths, areas, spans of time, velocities, or anything that can be quantified. They are misconceived as being more abstract. Yet what is their content? And what is their scope? They are altogether enshrouded in obscurity, even as to what people do with them, even to the people that use them as calculative devices. That is to say what calculus is the science of, or to say what algebra is the science of, as we can say that geometry is the science of shapes in and of themselves, or that arithmetic is the science of numbers in and of themselves. That is not of measured lengths and not of counting coins or anything else. To say what calculus and what algebra are the sciences of is very difficult. Whether even are they sciences of anything? Whether even are they sciences of anything? That is, whether are they sciences at all, rather than procedural knacks and calculation tricks, much like long division, which have no theoretical value. As that is, Socrates in the Gorgias says that rhetoric is not a science at all. He surprises Gorgias when asked what he thinks about rhetoric, what he thinks rhetoric is the science of. So rhetoric is not a science at all, but a knack or device. Rhetoric isn't the science of anything, but is a knack or a device. A sort of routine. And as long division is a sort of device or knack, a procedural trick for performing calculations. As long division is a procedural trick for performing calculations, but has no theoretical value. It merely happens to work, but even then blindly. So also might the procedures of algebra and calculus be procedural devices or knacks without theoretical value and without even a subject matter. As that is, arithmetic is the science of numbers, but accounting is an application of numerical procedures upon counted things. Since the symbolic notation of algebra and calculus may stand for anything that can be quantified or measured or counted, such as distances, speeds, areas, lengths, or weights, neither would they amount to pure mathematics, as mathematics is divisible into discrete numbers and continuous shapes. But those are the subjects of arithmetic and geometry, while algebra and calculus reach into processes far beyond discrete numerals and continuous shapes, but rather concern anything that can be counted, anything that can be measured. And seem to be mere procedural tricks procedural devices or knacks, as we don't know even how long division works. Long division is a sort of procedure that happens to work, but is arbitrary. The steps in the process of long division are arbitrary, or they seem to be arbitrary, or they are arbitrary in terms of whatever standard we might hold to explanation. That is, at least we can say long division cannot offer an explanation, cannot prove a theory. But again, theory. What a theory is something that has no place in these procedures of calculation. A theory is a premise and a conclusion. That all A is B. That all B is C. Therefore, all A is C. Sort of manipulating equations simply is not even within the range of what theories are, of syllogistic proofs. These things do not happen in algebra and calculus, but are most exemplary in geometry, in Euclidean geometry. But we, however, should leave that off for now. We are not in a position to answer that question without presenting a diversion. But what were the new sciences doing with the mathematical procedures of calculus and algebra? Or what significance have they with physics? For therein lies the subject matter of science, or the answer to those sorts of questions would place us over the target of the subject matter of modern science and mathematical physics. The speculative freethinkers of the 16th, 17th, and 18th centuries were less concerned with theorizing about general conceptual difficulties common to physics, which any philosophy of nature cannot leave incomplete. Any science of nature cannot leave incomplete, such as an account of generation and corruption, whether there be atoms in the void, whether motion be discrete or continuous, whether lengths of time be composed of discrete moments or are infinitely divisible, whether when water turns into air, one substance comes to be and another ceases to be, or whether a substance common to both merely undergoes alteration of quality, and so on. They were less concerned with those sorts of conceptual difficulties than they were with calculating with new mathematical procedures something or other that presumably is more relevant to mechanics. Those who did try to provide a groundwork for physics, most preeminent amongst them Descartes, Hobbes, Boyle, and the atomists, perhaps Gassendi, speculated in line with the content of that other concern that I have vaguely indicated. But this might be significant, that Thomas Hobbes was the only one of them that wrote a treatise of physics, De Corpore, which did cover the whole of physics and the principles of physics in a way that does contend with Aristotelian physics. But he is completely forgotten as a writer about these things, when the significance of Thomas Hobbes is in physics and mathematics. I guess they would rather not have us speak about his critiques of algebra than they would even have us talk about his political monarchism. And Hobbes even performed physics in the manner in which Aristotle outlined for the mixed mathematical sciences, whereby that something is so is arrived at physically, or by observation, or something of the manner. But why that is so is proved geometrically. One example is that it is a medical physician who provides us with the fact that something is so. That a round wound heals more slowly. The medical physician provides us with that is so. That a circular wound heals more slowly. But that is proved geometrically. But it's the ground of geometry to prove that is so, and why. Hobbes actually performed mathematics in that manner, physics in that manner. While Descartes also wrote about physics in a way that might be said to contend at least as falling within the same sorts of dilemmas or the same sorts of foundational inquiries to physics in a way similar to scholastic physics or to Aristotelian physics, but different in view. And Boyle also. Those are the only thinkers who even attempted to speculate about the whole subject matter of physics in a systematic and non-fragmented way. But why are they even disregarded? Those are the outstanding figures of physics. They're completely disregarded. Hobbes especially. But even then, they ignored the most foundational difficulties. They did treat physics in a holistic manner and considered conceptual difficulties, such as whether there be atoms in the void. They unraveled those difficulties, or thought them to be significant as obviously foundational to physics, and not falling outside of physics. Whether there be atoms in the void is a conceptual difficulty that does not fall outside of physics. The physicist doesn't go to the philosopher and ask if there are atoms. That is a matter for physics to consider. But physics is then a part of philosophy for the Stoics and for Aristotle. Even for the Stoics, physics was a part of philosophy. Whether there be atoms in the void. That conceptual difficulty, those figures, Descartes, Hobbes, Boyle, and Gassendi, knew to be foundational to physics as something having to be addressed. And as part of physics, as falling within physics. Very soon I will provide a quote by Leibniz regarding these very things and why they've faltered about whether there be atoms, why they're so concerned with corpuscles and explanations of phenomena in terms of particles. All of those figures, Descartes, Hobbes, Boyle, Gassendi, they're obsessed with talking about particles or corpuscles and explaining phenomena, macro phenomena in terms of the microscopic particles and their arrangement. Leibniz, in a quote that I will soon present, attributes the fault to their lack of combining metaphysics with mathematics, or metaphysics with physics, or their being materialistic or mechanistic. A groundwork was laid in physics by those sorts of thinkers that I have mentioned for what they were really concerned with, whether that be whatever that be which their calculated procedures were for. That groundwork, however, was primarily concerned with what they thought should be excluded from physics. Hence the peculiar accusation against scholastic physics of resorting to occult powers. Their accusation against scholastic physics of resorting to, quote, occult powers. And the equally peculiar response of considering all qualities as subjective phenomena in favor of a mechanistic explanation. Thus, most of these conceptual considerations at the foundations of physics were about what should be excluded that the scholastics are up to. As for foundations and first principles of science, they used the mixed mathematical science of mechanics as a model for how physics ought to be performed. At the time, mechanics consisted of geometric proofs of semi-physical problems, such as the balancing of unequal weights when extended from the fulcrum of a balance at different distances inversely proportional to their weights. That is the problem that unequal weights achieve equilibrium in a balance when the lighter one is placed at a distance proportional to their differences in weights, at a greater distance than the body of a greater weight. Rational mechanics at that time was also concerned with the principle of the lever, which is rather similar to that theorem, and things like the displacement of fluids and floating bodies. Accordingly, Fontenelle had written that, quote, physics has substance only insofar as it is founded on geometry. And S. Gravesend, as well as Descartes, and a great many others, took physics to be quite literally a branch of mathematics. Thus, from their perspective, hardly anything needed to be said about the principles of change and motion, or about any conceptual difficulties which are confounded in physics. The whole point seems to have been to avoid that sort of speculative reasoning by reducing physics to what can be mathematically formulated. Nonetheless, of the physical treatises which were composed, and which mentioned somewhat the principles of physics and conceptual difficulties, they were even then, without exception, referred to as mechanistic, or as the kind of physics that they were formulating is referred to as mechanistic physics. Again, I refer to Hobbes, Descartes, and Boyle especially. The only explanatory concepts they allowed were those which are relevant in the science of mechanics, things which can be quantified, such as weights, sizes, distances, speeds, angles, and the like. Those are the only concepts they allowed as explanatory principles. For rational mechanics already formed a sort of mathematical physics, much like the other mixed mathematical sciences, such as especially optics and astronomy. That's what they were modeling the new science after, these mixed mathematical sciences, which were in place and which are beautiful sciences. Optics, mechanics, astronomy. These are mathematical portions of physics. They treat only the mathematical aspects of things. Optics treats of rays of light only insofar as they are lines and insofar as they reflect at angles. It's the only thing that optics considers. The rays of light are lines, not particles or waves. In optics, a mixed mathematical science. Perhaps the standard of precision of an exact science appealed to them. But mind you, these were deductive sciences. And also Descartes, Cartesian physicists, people like Huygens, Malebranche, even Newton and S. Gravesend, all these 17th century figures, thought that physics should be performed deductively, should be mathematical for one and deductively proved. Because that is the manner in which Archimedes' mechanics is performed, and optics and astronomy. These are deductive sciences, mathematical, geometric deductions. Obviously, however, and I mean to say that sort of became corrupted into merely calculating equations. But both of those elements are prevalent at the time. Obviously, however, the sort of speculative thought regarding the principles of motion and change, which I've indicated as concerning conceptual difficulties, cannot be formulated mechanistically. Consequentially, they had nothing to say about whether motion be continuous or discrete, whether generation be different from or the same as alteration and qualitative change. Nothing to say about which motions are primary and which consequent. About what is required for there to be change at all. Whether elements and their qualities persist in their compounds or are destroyed upon being mixed. Whether some things be self-moving or anything like that. The one conceptual difficulty they do seem to have thought to be relevant and to have discussed at great length was whether there be atoms in the void, in which many of them thought there cannot be atoms as indivisible particles. But then they explained everything in terms of corpuscles or particles. So they're heavily influenced by this sort of atomism. And they were willing to conceptually mull over those problems and thought that one to be important, whether there are atoms in the void. Where they pretty much all of them came to the conclusion that there are particles and fluids. Part of the difficulty is the rearrangement of the categories of theoretical and practical sciences that took place, and the confusion of calling what was previously mechanics by the name of physics, or what was mechanics by kinematics, or to group all those together indiscriminately. And regardless whether Galileo's version of the new science is physics or mechanics or something else, the primary aim of algebra and calculus can in no way be theoretical physics in the sense of speculating about general concepts. I mean that algebra and calculus can have nothing to say about such problems as whether some things be self-moved. Algebra and calculus can have nothing to say about such problems as whether some things be self-moved, whether physical magnitudes be infinitely divisible or composed of indivisible parts, as atoms, whether intervals of time be composed of instances, and motions of indivisible parts. Algebra and calculus can have nothing to say about that, or any conceptual difficulty, whether there be atoms in the void. Incommensurately more work went into algebra and calculus than did physics in the sense of speculative natural philosophy. You will find that early scientific revolution, most of the achievements were in the invention of algebra and calculus. And those sorts of mathematical procedures were more so the epicenter of intellectual activity in the 17th century, even in the 16th century, and also in the 18th century. Yet again, calculus and algebra can have nothing to say about the theoretical framework of physics, about whether there be atoms in the void, or about what causes fire to move upwards and earthen bodies downwards. What could calculus and algebra tell us about the upwards motion of fire, and whether fire be pushed by something else or is moved by an internal principle of motion upwards? And the new science tends to be an aggregate of activity inseparable from the symbolic notation and operations of calculus and algebra, as of course presenting scientific theories, or rather scientific formulae, as algebraic equations. Scientists afterwards began to consider science to be some sort of procedure which couldn't begin until and unless the theoretical foundations are agreed upon. The scientists afterwards began to consider science to be some sort of procedure which couldn't begin until and unless the theoretical foundations are already agreed upon. That is, they speak as if they ought to be going forward without foundational questions about, for instance, whether bodies are infinitely divisible or are composed of indivisible parts, as atoms. And I think that was always the tendency of scientists. Few were willing to wait around to argue over first principles. Science has never been primarily concerned with physics as a theoretical or even speculative science. On the contrary, scientists are always bustling, or rather swarming, with compartmentalized activity, looking into the most hyper-specific details of minute facts, weighing and measuring and dissecting every feature of endless specificities with peculiar instruments, and compiling catalogs of data. But what experiment could have any say about whether magnitudes are indivisible, or about whether the efficient cause of the upward motion of fire is inherent in the body of fire, or if fire is pushed by something else upwards? Leibniz pointed out the deficiency in early modern physics regarding the conceptual foundations that have to be decided dialectically. This is a quote from Leibniz expressing much of what I've been trying to say. quote, "Now, this active force is exactly what best shows the distinction between the soul and mass, and in a way that can easily be sensed. For the principles of mechanism, from which the laws of motion derive, cannot be derived from something purely passive, geometrical, or material, nor proven by the axioms of mathematics alone. For in more than one article in the Journal des Savants of Paris, the Acts of Leipzig, and elsewhere, when speaking of his dynamics, and even more recently in his Theodicy, this author noted that to justify the laws of dynamics, we must have recourse to the real metaphysics and to the principles of fitness which affect souls, and which are no less exact than those of geometry." In the letters he exchanged with Hartsoeker, inserted in the Memoirs de Travaux, you can also find how he destroyed the void in atoms through higher considerations, even making use of part of his dynamics for this. Others, this is the important part of the quote, others who occupy themselves instead with matter alone cannot settle the question. That is why the new philosophers, who are ordinarily too materialistic and not trained to combine metaphysics with mathematics, have not been in a position to decide whether or not there are atoms in the void. And several have even been led to believe in them. That is, to believe that there are either a void with atoms, or at least that there are atoms swimming in a fluid that excludes the void. But he shows that void, atoms, that is perfect hardness, and finally perfect fluidity, are equally opposed to fitness and order. End of quote. Quote seems strange because these are sorts of letters or essays. Nor do I think that they ever cared one whit for what gets paraded as the scientific method. Recall that what is now considered as the scientific method was formulated in hindsight. It was not even mentioned in the 17th century. Nor could an experiment tell us if bodies are composed of atoms, or whether the efficient cause of the upward motion of fire is inherent and internal to fire, or is caused from without. Nor could an experiment tell us whether when water becomes air, whether one substance comes to be and another ceases to be, or if the same substance undergoes merely a qualitative alteration. Neither algebra and calculus nor experimentation can even feign to resolve those sorts of conceptual difficulties, which again are at the foundations of physics, whether there be atoms in the void, whether motion be continuous or discrete. These things have to be considered in physics. The closest thing they have to a method was Descartes' rules for conducting the mind, in which, quote, "the only definite problems are those in which ratios may be transfigured into equations." The only definite problems, Descartes says, are those in which ratios may be transmuted into ratios. Ratios may be transmuted into equations. That every definite problem should be treated thus, having, as he did, identified physics with mathematics. The general agreement was that physics must be performed mechanistically. That was at least something that they all agreed about. Or in the manner of the science of mechanics. That physics must be performed thus. And that was all they supposed themselves to need in order to formulate correlations between different orders of magnitude and quantity. Thus, scientific formulae are presented as algebraic equations. That, I mind you, is all in accordance with the Cartesian method illustrated in his rules for conducting the mind. However, over and above any method, what they did have was an instrument or a crafty device that is not their equipment for experimentation, but calculus and algebra, and nuanced mathematical procedures consisting of symbolic notation. And once again, Descartes is responsible for adapting algebra to non-arithmetical inputs, for adapting algebra to non-numerical inputs. What he called analytic geometry was the adaptation of algebra to line segments and areas, a crucial maneuver towards a mathematical physics. Afterwards, he specified that these mathematical procedures were meant not for the sake of mathematics itself. He specifically said that these procedures and these, in his rules for conducting the mind, these methods are not for the sake of mathematics itself, although he is employing mathematics, but for anything that can be quantified, such as angles of refraction in optics, weights and distances in mechanics, and a mathematical physics in general. Experimentation just about anything without the framework of a mechanistic physics and without algebraic equations could not amount to the procedures of science. What they have, and which is their only device, is their unique procedures of mathematical notation, the infinitesimal calculus and algebra. That is their only device. That is all they have. That they have had from the very start, and all propaganda about observation and experimentation is merely anti-scholasticism meant to deconstruct the prior order more so than to present what they themselves take to be their epistemological method.